Have you ever stopped to think about how we move massive amounts of energy, I'm talking natural gas, across thousands of miles? It seems pretty simple, right? Just a long pipe. But the physics that make it all happen, well, they're anything but simple. They're actually pretty amazing.
I mean, really think about it. How do you get natural gas from some remote field all the way across the country to a city to heat homes or power a factory? It's not like you can just stick it in a truck. No, you have to send it on an epic journey. And that journey, it takes place inside a pipeline. So today we're going to follow a little packet of gas as it travels down this pipe. And what you're going to see is that even though the path looks straight, the physics get complicated, and they get complicated fast. Okay, so let's get right into it, what we're calling the pipeline problem. Here's the deal. Moving gas isn't at all like moving water. Water is predictable. Gas? Well, gas is kind of like a diva. It has its own set of rules.
And here is the absolute core of the challenge. As gas zooms down a really long pipe, things like friction cause the pressure to drop. Now, for a gas, when its pressure changes by even a little bit, its most basic properties, like how dense it is or even its temperature, start to change right along with it. And just like that, a simple calculation turns into this dynamic, really complex puzzle.
So what is it about gas that makes it so special? Well, that brings us right to our next point. Gas doesn't follow the rules. And the biggest, most important rule it breaks, it's the one about staying the same density. The fancy term for this is compressible. A gas is a compressible fluid. You can squeeze it and its density shoots up. Let the pressure drop and it expands and its density goes way down. Honestly, this one single property is the main villain of our story, the thing that pipeline engineers are always battling.
The best way to get this is to see the contrast. Think about an incompressible fluid, like water. It's like a line of people holding hands. You push the person at the front and the whole line moves together, nice and predictable. But a compressible gas? Oh, that's like a chaotic crowd packed into a subway car. You can shove the people at one end and they just get all squeezed together. The person way at the back might not even move for a bit. The density changes all over the place and the whole thing is just way, way more complex.
Now, all this compressibility leads to a really strange side effect. As the pressure drops along the pipe, the gas expands and actually starts moving faster and faster and faster. But it can't just accelerate forever. Nope, it's about to slam into a very specific, very hard speed limit. And that limit is called sonic velocity. And yeah, it is literally the speed of sound, but, and this is the important part, it's the speed of sound within that specific gas, at that exact pressure and temperature. It's not some universal constant, it's the gas's own internal speed limit. It's the absolute fastest that any information, like a tiny pressure wave, can travel through itself. Engineers have a way to track this, and it's called the Mach number. It's pretty simple. Subsonic means you're going slower than the speed of sound. Supersonic means you're going faster. And Mach 1? That's the magic number. That is sonic velocity, and hitting it inside a pipe changes absolutely everything. Which brings us to this critical, crucial point. In a simple, straight pipe, like the one in our journey, you physically cannot go faster than the speed of sound. The flow just chokes. It's like the pipe hits its maximum possible flow rate, and no matter how hard you try to pull from the other end, you just can't get any more gas to go through. The journey literally hits a wall. Okay, so that speed limit is a huge deal, but it's not the only thing going on. There's another complication we have to talk about: heat. Yep, the temperature of the gas is also changing on its journey, and engineers have to plan for two very different scenarios. So on one hand, you've got what's called isothermal flow. This is where you assume the gas has plenty of time to trade heat with the ground or the air around it, so its temperature stays constant. This is a pretty good model for those super long pipelines. But then, on the other hand, you've got adiabatic flow. This assumes the pipe is perfectly insulated, so no heat gets in or out. This model is much better for short, really fast-moving sections. So how in the world do you keep track of all this stuff? Use this, the general energy equation. Now don't worry, we are not going to try and solve this thing. Just think of it like a master balance sheet for the journey. It accounts for every single bit of energy in the system. The energy from its speed, energy from going up or down hills, the energy packed into its pressure, and, super importantly, all the energy that gets lost to friction rubbing against the pipe wall. So, with all these insane challenges, compressibility, sonic speed limits, heat changing everything, how do engineers actually make this work? Well, let's take a look at the incredible toolkit they use to engineer the flow. Every journey has to start somewhere. And for our little packet of gas,
That beginning is a massive, massive push. To overcome all the friction and the pressure drops it's about to face, the gas needs a huge injection of energy right at the starting line.
And that big push comes from a compressor. A machine like this one works in a really powerful four-step cycle. First, the suction stroke sucks in the low-pressure gas. Second, the compression stroke squeezes that gas like crazy, which skyrockets its pressure. Third, the expulsion stroke shoves that high-pressure gas out into the pipeline. And finally, any leftover gas expands, and the whole cycle starts over again. Boom, boom, boom.
Okay, so the compressor gets us started, but what about that pesky speed limit we talked about? We know a simple pipe just chokes up at Mach 1. So what if you need to go faster, say in a jet engine or a rocket? How on earth do you break the sound barrier?
You use this absolutely brilliant piece of engineering, the converging-diverging nozzle, also known as a Laval nozzle. Its very specific hourglass shape is the secret to manipulating compressible gas in a way that almost seems to defy logic.
So here's how it works. As the high-pressure gas rushes into the first part, the converging or narrowing section, it picks up speed. It keeps accelerating until it gets to the skinniest part, which is called the throat. And right there, at that one precise spot, two incredible things happen. The gas hits exactly Mach 1, and its pressure just plummets.
And now for the magic. Once that flow hits Mach 1, its properties completely flip. As it enters the second half, the diverging or widening section of the nozzle, something totally counterintuitive happens. Instead of slowing down like you'd expect, the gas continues to accelerate, blasting right past Mach 1 and going fully supersonic. It's just a brilliant example of how a simple change in shape can overcome a fundamental barrier of physics.
So let's just quickly recap our pipeline journey. We learned that moving gas is tricky because it's compressible. We saw that its flow in a regular pipe is capped by its own internal speed of sound, or Mach 1. We found out that heat transfer totally changes the math. Compressors give the gas that initial push it needs to get going. And finally, these incredibly clever nozzles can use physics to smash right through the sound barrier.
And you know, the physics we've talked about today aren't just for pipelines, not at all. These are the fundamental principles that power jet engines, that launch rockets into outer space, and that make countless industrial processes work every single day. The simple journey of a bit of gas in a pipe is, when you think about it, a window into some of the most powerful technology we have ever created.